finding factors and then making that connection. So, sorry. So what is the factored form of this function? We'll do it the long way. So the front number here is a 1, right? Okay, so I'm looking for two numbers that multiply to 1. I don't have a lot of choice there. And then 8 is probably 4 and 2. Yeah. Then one of them has to be negative. Let's try this one. So I get a negative 4 plus 2 is a negative 2. So 1x plus 2, 1x minus 4. So the factored form would be x plus 2, x minus 4. All right. So how does that help? Well, it would help find x-intercepts, wouldn't it? Because x-intercepts occur when the y is 0. So that means I get a negative 2 as one of my zeros and 4 as my other 0. So far so good? Well, that's a location. A negative 2, 0 is a location. So is 4, 0. So let's graph that. Negative 2, 0 would be here. 4, 0 would be here. We'll go one tick mark to the right and to the left of that. What about end behavior here?
It is same.
Right, because it's an x squared, right? So we're going to do this because it sort of acts like an x squared. There's more. So it's even, which is the same, and the leading coefficient is positive. So since the leading coefficient is 1, this thing goes up. Okay, so today when I ask you about end behavior on your homework, you can do it the cheap way. You don't have to write that whole definition again.
Wait, acts like what?
Acts like an x squared. I know it's not x squared, it's x squared minus 2x minus 8, but it acts like an x squared. So that knows, now we know it's even, the same end behavior, so they go up. Alright, well, if it goes up here and here, then I think I'm good. I can graph this thing.
And it doesn't matter where it goes down on the bottom?
Not today. Are you worried about it?
Yeah.
There, instead of negative 8.
Does it matter?
No, I don't care. Is my vertex about right? What do you think?
The vertex is at 1 negative 9.
Okay, so I'm pretty good, aren't I? Good. It really doesn't matter too much, guys. Most of the time when you graph stuff, the intercepts are important. Well, this one and this one are we needed to find. This one you can read off in the formula. And if you wanted to find this, you can also do that, because when we did this with our boxes, just not too long ago, didn't we do like a derivative, and we found that you can find this x location by doing that, because not all of these are going to be parabolas. So, you know, you can just do that. Any questions? So now we're going to add to it, obviously. Okay, moving on. So here's a third degree polynomial. How do I know it's a third degree polynomial?
Because of 3 x's.
Yeah, there are 3 x's. So this is my symbol for x like. This acts like an x cubed. That's a third degree polynomial. Where are your x-intercepts? Well, keep in mind again that that would come from, I'm not going to do this for all of them, but when is x plus 1 equal to 0? When x is?
When x is
Negative 1.
-1, or 3,
or 3 or
or
negative 4.
-4. Well, then these are the dots on my x-axis, aren't they? Okay? How about end behavior? Well, since it acts like an x cubed, that makes it an odd function. That means it goes in the opposite direction. So for opposite, I just want to worry about the right side. So on the right, what does it do? On the right side, this one is going to go up, because the leading coefficient is still 1. The leading coefficient, since you cannot see it, is out here. It's 1. That's positive. This thing needs to go up on the right, so that means on the other side it goes down. I'm ready to graph. I needed a dot at a -1, -2, -3. I need a dot at a -4. and I need a dot at 3. Okay, I'll make it go 1 on either side. And then I mark my end behavior. So on the right side, this thing goes up, right? Yes?
Yes.
And on the left side, it goes down. I work better from left to right. So I'm going to start, so it goes down here. So I'm going to start over here. We'll make it wiggle. Make it wiggle some more. And there you go. That's a reasonable graph.
Does it matter how deep it goes?
No.
There?
I don't, notice I'm not even marking the y-axis because it doesn't matter how deep that thing goes. Okay, what I don't want you to do is, don't do this. I mean,
Oh, yeah.
technically, you're not really wrong. Okay, just make it wiggle a little bit. Okay?
Make it move.
Yes, just show that it does go up and down. All right. So same thing here. So the -4 becomes a,
If it's negative,
makes a 4. The 2 becomes a -2. The -3 is a +3. The +5 should count as a -5. So these are the dots. How about your end behavior? This one's going to act like what?
this is going to act like x cubed. X to the fourth.
X to the 4th. And then I'm going to list a -2 here as well, because this is the first one where the leading coefficient is actually there. So x4 means even, right? So it's the same end behavior. And it both goes down. So both will go down because of the -2. Okay, and since this, so this doesn't graph like the stuff from yesterday, I don't even have to worry about dots on the y direction. So let's see, what do we have? So -5, so 1, 2, 3, 4, 5, 6, 1 past it, -2, 4, 1, 2, 3, 4, and 3. Both of them go down, right? Yep. So down here and down here. I work better from left to right. So 1, 2. There we go. I missed this one, so make it dot a little bigger, and then it's good. That was it. Anybody have questions on this? You want me to erase it? Yeah.
So for the vertical in the on the top and the bottom, you can draw whatever you want.
Pretty much. Since so many are so concerned about that y value, okay, one of the y values is easy to find. The intercept is actually the multiplication of the 1, the -3, and the 4. So 1 times the -3 is a -3 times 4 is a -12. Look, it crosses right there, the -12. This one, and you'll see now why I don't really care about the y's anyway. So for this one, I'd be a -4 times 2 is a -8 times a -3 is 24 times 5, it's 120 times a -2, that's a -240. This represents a -240. The y-intercept, all that stuff doesn't matter one bit. On this graph, the most interesting parts are here, 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 and here, the x-intercepts, which you have to find. This one, which I don't need to graph it to find it, I can just do a little simple math. And then all the other points would be that would be interesting would be here, here, and here. Well, how do I find that? How would I find these? We're not doing that this year. You did it for me with the boxes and the maximum volumes. These would be found by using the derivative. Well, we don't need to do that yet because we're not finding derivatives. But it's not that hard to find a derivative for this thing. And then you just solve it for 0. Well, that's for another class. Okay? All right. So how about this one? So this represents a slightly different change because notice that I do have 2 factors. So this one gives you an x-intercept of 2, but what about here? What are the x-intercepts here? Well, that's a quadratic, isn't it?
But it's not factorable.
It's not factorable, so how would you find them?
Quadratic formula.
Yeah, we can do the quadratic formula. So we're going to do that below. So negative 1 plus or minus the square root of b is 1. So that's 1 squared. That's 1 minus 4 times 1 times 5 divided by 2 times 1. So that's a negative 1 plus or minus, what is 1 minus 20?
1 minus 20,
Negative 19 divided by 2. So what does this mean with this being a negative square root? Right, there are no more, and since solutions is the same as saying what in this case? X-intercepts, no more X-intercepts. Okay? Okay, I'll work with that in just a second. So, at this point, my best guess would be that this is going to happen. And we won't graph these today at all. So, but this one would go through 2, right? It's a third degree, so it should probably have 2 humps, shouldn't it?
Yes.
Well, since I'm out of room below here, I'm going to make my 2 humps up here. Okay, this is my best guess. I don't know if that's true at all. So if you had this, then there would be something else you'd have to do to graph this stuff. Basically, you're going to make a table. But, okay. So I'll get back to that in just a second and tie it up over here. So if you have a negative under a square root, that's considered an imaginary solution. What that means is that you can take out that negative and write it as an I. I stands for imaginary. Does that make sense? So the negative 1, the square root of a negative 1, that's just considered, we're going to call that I. That's an imaginary answer. So if I only have one intercept here, then the other 2 intercepts must be what? Apparently they are imaginary.
Yeah, imaginary.
They don't exist. Because imagine that this happened. What if I move the x-axis? Could I have 3 intercepts?
Yeah.
Yeah, well, we move the x-axis below the wiggle. Or we move the x-axis all the way above the wiggle, only creating 1. So I could have had this picture as well, where the intercept occurs here and then the wiggles occur below. So they're imaginary. So imaginary numbers have something to do with imaginary intercepts. Okay? Alright. So that part of that is for next week. We're going to talk a little bit more about imaginary numbers, where that comes from. Alright, so this problem requires you to do a little work on your own. You should be able to factor this problem. Unfortunately, I did it earlier today, so I won't mess it up again. So the end one is a pattern, x minus 2 and x plus 2, right? Alright, and then this one, if that's a negative 6, we make this a plus 6 and then a negative 1. Okay? So then that's factored. Okay, so what does that mean? Well, that means that you have what for your x-intercepts?
Negative 6, positive 1, positive 2, and negative 2.
Okay. How about end behavior?
It acts as x cubed, which is,
Not an x cubed. This acts like a 1x to the 4th, doesn't it? So it's the same end behavior because it's even. Sorry. Yep. And since it's a positive 1, it means it has to go up. Well, you're ready to graph. 1, 2, 3, 4, 5, 6, and a little bit more. We have a dot at a negative 2. We have a dot at 1. We have a dot at 2. And both of them go up, right? And there you go.